1, 2, 2, 2, 1, 2. So I might be a little bit lower than that, but something like that maybe. 1, 2, 2, 2, 1, 2. I don't know. I don't know what the live stream device is like. Do you have like headphones or anything? Do you have meters on there? Oh, okay. Yeah. Honestly, yeah, and honestly, Zoom, like their compression and uh yeah, the algorithms they use are like even with a low feed, it's like it's kind of scary how good it works. So the live stream is working still. Um, Oh, like the Zoom audience here? Yeah. I already checked this one. So I heard it through yours. Yeah, I heard it from. It's just one line. Right. 1, 2, 2, 2, 1, 2. These ones I might bring down a little bit. 1, 2. Am I hearing the echo from you, or is that something else? You're welcome. Two, 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 1, 2, 3, 4, 1, 2.
You can turn it up, but you can do that for.
Test 1, 2, 2, 2. Do you have headphones? That's the best way to monitor so that you're not in the room. Yeah. I might even have some if you want them. I mean, it's probably not necessary for this, but am I getting, is it just a slap back in the room? 1, 2, 2, 2, 1, 2. No, sorry. Eating myself.
Yeah, you're set to eight.
Yeah, the input is Do you have output going? The speakers are muted? Because I thought I heard. No, speakers are muted as well? Okay, perfect, perfect. Because just especially right, it won't matter as much once you start speaking, but then you get like the mic starts picking that up and then it just creates a loop. 1, 2, 2, 2, 1, 2, 1, 2, 2, 2, 1, 2, 3, 4, 1, 2, 3, 4. Okay. Happy.
fine, yeah. Okay, so should I? All right, good morning, everyone. My name is Arun Parmekanti, and I'm a condensed matter faculty member here in the physics department, and it's my pleasure to welcome you all to the second day of our Welsh lectures in physics. So yesterday we heard two fantastic public lectures from our speakers, Professor Alan Aspey and Professor Steve Kivelson, who gave us insight into how quantum entanglement plays such an important role in quantum mechanics and how it shows up in the physics of photons and correlated electronic systems. And today we'll hear more colloquium style talks from the two of them. So the first talk is now by Professor Kivelson, and the second talk will be at 2 o'clock by Professor Aspey. I thought it'd be nice to have Professor Heyang Ki, who's here in the audience, to introduce Professor Kivelson because she's been his longtime friend and collaborator. So I thought it would be appropriate. Thank you.
Yeah, so my name is Heyang Ki, and I wasn't sure if I can make it due to our family issues, but given that I'm here, it's my great honor to introduce my old friend and my former supervisor, Steve Kivelson from Stanford. Yesterday we heard his bio, so I don't want to repeat. Instead, it's because you can find them in Wikipedia. When he graduated Harvard 1979, and then moved to UC Santa Barbara as a postdoc, right? And then 1982, he joined the Stony Brook, where he had a fantastic physicist, some of you probably already know. And then he moved to UCLA 1988, and then moved to Stanford in 2004. I was a postdoc from 1998 to 2001 before I joined the University of Toronto, and I was lucky enough to be one of his postdocs. Yeah, so as I said, that's what you can find in the Wikipedia. So I'll tell you one small story that you probably cannot find on a Wikipedia. That you better to be careful what you say. So Steve is, as you can tell, he's always smiling and very kind of favorite person among the young people, like a student and postdoc. He was always crowded by us, and one of them is me back then. So I asked him, he's someone who is very insightful. So I asked him, where do you get an idea? And his answer was that, well, actually, ideas are very cheap. So what he values more than idea is that how you test your idea in actual experimental lab. And that actually made me kind of my research direction towards I'm a theorist who really, kind of linked to the experimental situation. So in that sense, he has made a lot of many people given the career paths, had changed some of the career paths. So with that, my little story, please join me in welcoming our first speaker, Steve Kivelson.
Yeah, it's always scary when somebody remembers something you said, but that didn't sound so bad. I don't remember it, but okay, it sounds good. Yeah, so I'm afraid today's talk is going to be a little less polished than I would like. I somehow misunderstood. I thought I was giving a technical seminar, so I've quickly scrambled, and so I'm not going to be talking about precisely what I was advertised as talking about, but okay, I hope you'll find this interesting. I'm going to start by reviewing some well-known aspects of the physics of solids, in particular the physics of metals, to set up the second half of the talk where I will introduce you to some of the big puzzles that are vexing the field and some ideas on how to address those. So the first part of the talk is going to be all old things, but I hope that I can bring some new insight, some new perspectives to it. So I'll be talking about metals, strange metals, and bad metals. And the work, the original work I'll describe is in collaboration with current postdoc, Chaitanya Murthy, the next student, Ilya Esterlis, and a current student, Akshat Pandey. So let me start by reviewing some aspects of the physics of conventional metals, which is so simple that when you learn it, it seems really boring. But if you look back at it, it's actually really incredible that it works, and works with, well, an amazing precision. So, and then, as I said, I will tell you some ways that highly correlated metallic systems fail to behave in the ways we understand. And in particular, there's been an idea that's circulating in the condensed matter community and actually also in the quantum information community that have sort of met, which is that maybe what's at play is some universal Planckian bound on thermalization in quantum systems. And what I'm going to do is to argue that that's probably not the right perspective, that there is a different perspective that can explain the same phenomena, but that involves a rather different sort of bound. Okay, so let me start by summarizing some aspects of the Landau-Fermi liquid theory of metals. So the underlying proposition here is that at low energies, the properties of a metal are equivalent to the properties of a gas of non-interacting fermions. Okay, and of course, non-interacting problems are problems we can really solve. So once we make this outrageous proposition, then everything is simple and seemingly boring. You know, it's not that everything is completely simple. The dispersion relations may be complicated. Instead of having the dispersion relation of free electrons, there will be some dispersion relation consisting of bands, and instead of k being momentum, k becomes the block wave vector. But other than that, it's non-interacting electrons, just with some new dispersion. And of course, this whole perspective derives from the notion that electrons are waves. This is deeply quantum mechanical. By non-interacting electrons, we've emphasized the quantum mechanical aspect of electrons rather than the classical properties of electrons. We almost don't see that the electrons are propagating through a dense array of atoms. All that does is give us some modified dispersion relation for the electrons. Okay, so I said that. And actually, often these dispersion relations can be computed quantitatively using density functional theory. It's not at all obvious why that is. This is a rather extreme approximate scheme, but just empirically, it does seem to work fairly well. But the main thing that comes out of this perspective is the existence of a Fermi surface. So let's look in momentum space, since this is a highly quantum mechanical problem. And for instance, if we had free electrons in 2 dimensions, then the ground state would have all states with momentum less than a Fermi momentum occupied by 2 electrons, and all states outside that empty, and there would be a sharp surface in K space that is the boundary between the occupied and the unoccupied states. in realistic three-dimensional systems, this Fermi surface can be much more complicated. Here's a picture of the Fermi surface of copper. I'll tell you what these arrows mean later, but you know, it's some complicated shape, but it has the feature that it has an inside and an outside, and it's the sharp boundary between occupied and unoccupied states. And many properties of metals follow from that statement. So before we go on, let's just consider how ridiculous this statement sounds. The electrons in a solid are extremely strongly interacting. There is no sense in which the Coulomb interactions between electrons is any weaker than their Fermi energy. In fact, in some fundamental sense, they satisfy the virial theorem. So the interactions are twice as strong as the kinetic energy. At any rate, there's no way that they're weak. And not only that, this is a really extremely strange and unusual state that we're describing. It has an enormous density of gapless modes in the system, far more than in any other system that you can think of. In other systems, maybe you have gapless modes at some point in K-space, but here you have gapless modes at entire surfaces in K-space. And that means that you might think there are all sorts of instabilities, all sorts of ways the system can lower its energy by rearranging the degrees of freedom and opening gaps. And indeed, there is, from perturbation theory, we know that the Fermi liquid state is only marginally stable. It has an instability to superconductivity, but it's a marginal instability. It's only a logarithmic effect. And so in many cases, this is suppressed to extremely low temperatures. And from a modern perspective, it's the most highly entangled ground state phase of matter known to humanity. It doesn't have an area law entanglement. It has a logarithmically larger entanglement in its ground state, unlike anything else except possibly a quantum critical system. So it's the world's most entangled phase of matter. Now, that's the ground state, but you know, even at room temperature, typical metals are really very close to being in their ground state. The typical scale of energy in a metal is set by, well, fundamental constants of nature. It's on the order of a Rydberg, which is 100,000 degrees. So even at room temperature, in dimensionless units, a metal is at a reduced temperature of 3 × 10⁻³ or something like that. So whereas cold atom systems are colder, in dimensionless units, no cold atom system has ever come close to copper at room temperature. And you know, then you would do dimensional analysis and you would imagine that, say, the free energy would be the ground state energy plus corrections that are of order T over EF squared. So corrections should be small. And this is indeed what one finds. This is the famous Sommerfeld expansion. For instance, this gives rise to the linear specific heat of metals. So, okay, this is an outrageous proposition. There's actually no way to show that this is right from first principles. We can show perturbative stability of the Fermi liquid, but starting from strong interactions, I don't think there's any convincing theoretical way to show that this is right. We're sure that this is right because it's been confirmed in experiment. And let me give you an example of one of the most spectacular emergent phenomena of all of physics, which is the best way that we know that this is all right. So let's look at the magnetic field dependence of thermodynamic quantities, for instance, the free energy. And by similar arguments that I gave for the temperature, you would expect that, well, okay, this should be governed by the quantum of magnetic field. And the quantum of magnetic field is the amount of magnetic field you need to make a flux quantum through an area on the order of the Bohr radius. And so that comes out to be something like 10,000 Tesla. So you would think that the susceptibility, which is the second derivative of the free energy with respect to magnetic field, should go like an quantum of energy divided by a quantum of magnetic field squared, which is small in proportion to the fine structure constant squared. And indeed, that's roughly right. Most materials have no magnetic response to speak of. That's the fine structure constant. And so we would expect the magnetic response of most solids to be weak and featureless. But that's not what we see when we take crystalline metals down to very low temperatures. What we see are quantum oscillations. We see oscillations in both thermodynamic and dynamical properties as a function of magnetic fields, hundreds, thousands of these oscillations with field scales that are teeny compared to the quantum of magnetic field. And this is really quite spectacular. It's not only unexpected undimensional analysis, it's non-analytic functions of the parameters. And that's something that we generally think only happens at critical points. And in fact, here, this behavior doesn't involve any of the fundamental energy scales of the problem. It turns out to be a scaling function of the magnetic field divided by the temperature. So the lower the temperature is, the more structure you find here. Okay, the understanding of this is as follows. If you think about the motion of electrons in a magnetic field, we can think about semi-classical dynamics. They obey the Lorentz force law. This has a couple of constants. Oh yeah, where the velocity here is whatever the velocity is from the band structure of the solid. So it's a little different from the dispersion in free space. But other than that, this is the familiar Lorentz force law that, among other things, has the implication that the component of the momentum along the magnetic field is a constant. So the electrons move along contours of constant k in the direction perpendicular to the magnetic field, and that the energy doesn't change with time, so the electrons move along contours of constant energy. And so that's what these arrows are showing. These are for a magnetic field perpendicular to this. The electrons move along contours of constant energy, and so they encircle the Fermi surface along these contours depending upon the orientation of the magnetic field. And then if we go beyond classical mechanics, these orbits can be quantized, as was shown by Onsager, and the quantization condition tells us that the area enclosed by this orbit, so that's the area in k space, times the flux quantum over b is equal to 2 pi times an integer. And so that's what we're seeing when we're seeing quantum oscillations here. We're seeing magnetization oscillations that are periodic in 1 over b. So they're non-analytic. There's an essential singularity at b goes to 0. This period here tells us about the period of the Fermi surface in directions perpendicular to the magnetic field. So we can map out the full geometry of the Fermi surface. There are 2 amplitude factors. The first one is a temperature-dependent factor, which turns out just to be the Fourier transform of the Fermi function. So this where this characteristic temperature is determined by the effective mass of the electron on this orbit. So this temperature-dependent factor directly measures the fact that the excitations in our system are fermions. We don't have to take that from theory, that's directly from experiment. And well, finally, there's something called the Dingle factor, which I won't talk about, but it tells us further information. It tells us about the lifetime of the quasi-particles. Okay, so here, when we look at this set of quantum oscillations for copper, it's telling us that this notion of the Fermi surface, which comes from simply ignoring the interactions between electrons, this amazingly simple picture, maybe naively simple picture, turns out to be an extremely accurate description of the properties of most metals. Okay, let me turn to the resistivity, which is where new things are coming. So there are many things that you would like to measure about materials besides the resistance. In fact, I would prefer to think about almost anything besides the resistance. I'm a thermodynamics guy, and so I would like to be thinking about equilibrium properties of systems. The resistance depends upon dynamics, on relaxation processes, and so it's extremely complicated. But it turns out that most discoveries in condensed matter physics historically come from measurements of the resistance, and it's one of the things that can be measured with the greatest precision. And so if we want to understand the quantum properties of solids, we really have to think about resistance. We're forced to. It's not as bad as it sounds. We can measure the resistance. The resistance is a symmetric two tensor. It depends on many control parameters: temperature, magnetic field, concentration of alloys, strain, pressure, whatever. And this can be used to extract information. And in fact, roughly the definition of what we mean by a metal is something whose resistance remains finite in the limit as the temperature goes to zero. So even in defining this state of matter that we call a metal, we have to think about the resistance. Okay, so let me do dimensional analysis on the resistivity of a material, just like I've done for everything else. This is familiar in two dimensions, where the quantum of resistance is just Planck's constant over E squared, but we can make a quantum of resistance from fundamental constants of nature in any dimension. In 3 dimensions, we have to multiply this by a length scale, and the only length scale available for dimensional analysis is the Bohr radius. So this is the quantum of resistance, and this is 135 microohm centimeters. So that's what you would guess the resistivity of a material was if you knew nothing. And actually, that's an interesting number. That's roughly the number of any non-crystalline metal you would encounter. If you look at liquid metals or amorphous metals, they all have resistivities which are within a factor of 2 of this. So nature really does notice this dimensional analysis. Good metals, on the other hand, have resistivities that can be 1, 2, or more orders of magnitude smaller than this. And that's an emergent feature that comes from having a long mean-free path. If we look at the Drude theory of conductivity in metals, we find that the resistivity is equal to this combination here. Lambda F is the Fermi momentum, but the Fermi momentum is typically on the order of a Bohr radius, times 1 over KFL. KF is the Fermi momentum. L is the mean-free path of these electrons, which is determined by scattering off impurities or phonons or other electrons. And this can be long, and that's why the resistivity of metals is often bigger than the quantum of resistance, smaller than the quantum of resistance. So, so good, directly from the measured resistivity, we can ask questions about what sorts of theoretical approaches to this problem might conceivably be consistent. So for Landau theory to be valid, the lifetime, the decay rate of the quasi-particle should be small compared to its energy, which means that this scattering rate should be smaller than the temperature. And that means that the resistance must be smaller than the quantum of resistance times the temperature over the Fermi energy. And that's an extremely restrictive condition. Most metals, this condition is actually violated. There's a much weaker condition for Boltzmann transport to be valid. I at least would like that the scattering rate is small compared to the Fermi energy so that I can locate quasi-particles somewhere on the Fermi surface, and their momentum is at least defined well on the scale of the Fermi momentum. And that then simply requires that the resistivity be small compared to the quantum of resistance. So I want to stress these are not physical bounds, these are theoretical bounds. These are bounds on what sorts of theoretical constructs we can have in mind. The material itself, of course, can violate whatever bounds it feels like. Ask me sometime about Hinckam's dictum. So this is a statement about what sorts of theories are valid. Okay, so there are many sources of scattering of electrons, but in clean materials, it's mostly determined by electron-phonon scattering. And there's a beautiful theory of this, which is the Bloch-Grundhuisen theory, which tells us that the scattering rate is some dimensionless measure of the electron-phonon coupling lambda times a scaling function of the phonon frequency divided by the temperature. And this number is 1 at high temperatures, and it goes like 1 over x to the 4th at low temperatures. This high temperature regime, where the scattering rate is linear in temperature, was described long ago by Prange and Kadanoff. And what they pointed out was there's a rather interesting regime in solids where the temperature is small compared to the Fermi energy, which means that the electrons are highly quantum mechanical objects, effectively in their ground state. But above the Debye temperature, the characteristic phonon frequency, so the phonons are entirely classical objects. So this is an interesting range of temperatures. It exists because of the large ratio between the ionic mass and the electron mass. And in this region, we get this T-linear resistivity with a slope that's proportional to the electron-phonon coupling lambda. Okay, and so here's copper, and you've just understood why the resistivity of copper is linear, and by the way, why its value is so small compared to the quantum of resistivity. Lambda can also be measured, so lambda can be extracted from the slope of the resistivity in this regime. It also enters into the theory of superconductivity in ways that I won't describe, but by tunneling into metals in their superconducting state, one can also directly measure this quantity lambda. Here's lambda for what used to be called a high temperature superconductor, one of the A15 superconductors, niobium-3 tin, where lambda turns out to be 1.78 as extracted from tunneling. And so I said that we understood this theory. Here's a table that sort of illustrates that. So here's a bunch of metals. This is from a nice review article by Phil Allen. Here's the value of lambda extracted from the resistivity, the T-linear resistivity at high temperatures. Here's the value of lambda extracted from tunneling into the system in the superconducting state. And here's the value of lambda extracted from local density approximations, DFT calculations. And okay, actually in theory, these lambdas are all slightly different averages over the Fermi surface. And there's no reason they should be exactly the same, but you can see they all more or less agree with each other within 10 or 20%. So this is really a problem that we understand. How much time do I have now? What? 30 minutes? Okay, good. Okay, so this is great, but there are many metallic systems that exhibit measured quantities that can't be understood in this framework. So let's turn to those. They're bad metals. These are metals in which their resistivity is bigger than the quantum of resistance. And so none of the theoretical constructs that I've described can describe these metals. They're strange metals where the resistivity, T-linear resistivity, is not surprising. I just showed you it was ubiquitous, but this remains T-linear down to way too low temperatures, way below the quantum of vibration, way below the Debye temperature. And they're Planckian metals which have a resistivity that are too appealing to theorists to have any such explanation. Okay, that's maybe a little bit glib, but it's an idea that's popular with theorists, and where the idea is that maybe you should think about the resistivity in an entirely new and different way, rather than thinking about what the actual mechanism for the relaxation of the current is. You should understand that there's some fundamental upper bound on the rate at which things can relax to equilibrium, and you're bumping up against that bound. And when you bump up against that bound, maybe the details of the mechanism don't matter. And that's a very interesting and profoundly new way of thinking about transport. So actually, all of these ideas emerged from trying to understand data in the cuprate high temperature superconductors. All of these things now have been identified in many other systems, but let me just show you the sorts of things that one sees in the cuprate high temperature superconductors that led to these ideas. So here's the resistivity of optimally doped lanthanum strontium copper oxide. Here for comparison is the resistivity of that very same niobium-3 tin on which I showed you tunneling data. What you see is that the quantum of resistance is sort of not noticed by the lanthanum strontium copper oxide, whereas for the niobium-3 tin, it's doing something that can be actually well described by Bloch-Grunhausen theory until it gets to be on the order of the quantum of resistance, and then it sensibly crosses over to do something else, which is called resistivity saturation here. Don't be confused. The fact that it's been named doesn't mean that we understand it, but at least this material is accommodating to our theoretical prejudices, and when it goes from a regime where one sort of theory works to where it doesn't, it shows a crossover. But lanthanum strontium copper oxide really pays no attention to our sensibilities. Here are a couple of other materials which we'll return to in a minute, but here's more modern data on lanthanum strontium copper oxide, this time at concentration 0.19, designed to have the longest regime of T-linear resistivity. And what you see is this beautiful T-linear resistivity. It doesn't pay any attention to the quantum of resistance, and it doesn't pay any attention to the fact that there are various phonon modes that are freezing out as we cool through this. So it's just not doing anything it's supposed to do. That's a straight line through the data. You can't actually see what happens here at low temperature, but you can access that by going to very high magnetic fields, high enough to even suppress superconductivity in the cuprates. That's what's shown here. And okay, there's the T-linear we looked at. There's also a T-linear behavior at low temperature. It's probably a different T-linear behavior. This curve certainly makes it seem that way. But here is, so here on one curve, we see a bad metal that ignores the quantum of resistance, and we see a strange metal that seems to continue T-linear all the way down, two behaviors that we just don't have a theoretical framework for. Okay, good. So here's just the definition of things we don't understand. Bad metals have a resistivity that continues to temperatures past where any quasi-particle description at all should be valid. Strange metals have T-linear dependence of the resistivity that continues to temperatures well below any characteristic phonon frequency. Okay. And Planckian metals are ones where the resistivity is described by a transport rate that satisfies some bound, which is conjectured to be that the scattering rate is equal to a number of order 1 times the temperature. Okay, so that's the things we're going to be thinking about. Oh, come on. So one idea that goes way back is that maybe some of this reflects proximity to a quantum critical point. This idea actually is already present in the very earliest days of high temperature superconductivity in the work of Chakravarty, Halpern, and Nelson, and they drew a putative phase diagram like this with some quantum critical point where you go from antiferromagnetism to a quantum disordered state. And they pointed out a number of things about quantum criticality. One is there are no quasi-particles. There's no energy scale. Because of that, any emergent energy scale, like a scattering rate, must be linear in temperature. Actually, this coefficient should at least be universal for different critical points. And so that sounds pretty attractive, and maybe that's even seen. And here's some data on strontium ruthenate 327, tuned with magnetic field to be very close to some sort of unidentified quantum critical point, but you can see that it's a quantum critical point because there's sort of a logarithmic divergence of the specific heat coefficient, and you see this very T-linear resistance that's interrupted in this old data by some phase transition, but in more recent work from Steve Julian, they've managed to extend this down to still lower temperatures. Okay, so maybe this is in some ways associated with a quantum critical point. That's a linear fit to the data. But that can't be the basic answer to this problem. It might be in certain special cases, but this sort of behavior I've described occurs very broadly in highly correlated systems. It occurs when there's no other evidence of any sort of quantum critical correlations. And there really isn't any good theory to compare it to anyway, because the theory of metallic quantum critical points is a mess. And it, moreover, doesn't say anything about bad metals. So we need new ways of thinking about this. Now, there was another really dramatic step in this field, this paper in Science by Andy McKenzie and collaborators And what they did was they looked at lots of materials and found where they had T-linear resistance and estimated what the coefficient alpha was, that is to say, the ratio between the scattering rate and the temperature. And this line here is alpha equals 1. And here's data on lots of interesting materials. And among other things, here's some typical cuprate high temperature superconductor. And the fact that so many different materials are clustered near here sort of suggested that maybe really there's a bound at work here. And this has been advocated by a lot of people with a lot of interesting work, most notably by our recently deceased colleague, Jan Zanen. Here is a charming paper that I refer you to that articulates the arguments for this sort of perspective. Okay, so here's what we noticed, is that sitting out here were lots of conventional metals. And I just told you that we really understand everything about these. So we should understand what they're doing there. And okay, we come back to this table, and there's something that I have noticed for all my life, all my physics life, that didn't seem to bother anybody else, but bothered me, which is, why is lambda never bigger than 2? And you know, I assure you it's not because people haven't looked, because there is also an idea that the superconducting TC is a monotonically increasing function of lambda, so people have spent enormous effort trying to find lambdas bigger than 2. And okay, so you see, you know, lambda is a dimensionless constant, so it's of order 1, but sometimes it can be pretty small, like in calcium, it's 0.05. But it's just never bigger than 2. In fact, it's never bigger than 1.75, as far as I know. Why is that? So we propose that that's the bound that's at work, is the reason you never see lambda bigger than 2 is at least the explanation for why this lambda seems to satisfy a bound for conventional metals. So let me go through this. This is a little more technical, but we're going to look at a model of the electron-phonon problem. And because of, you know, most interacting problems with electrons can't be solved numerically because of the famous fermion minus sign problem, but it turns out this problem doesn't suffer from a fermion minus sign problem. So it can really be studied numerically extremely accurately. And so we can make declarative statements actually without any theoretical prejudice. So we take the electrons to be some tight binding model on a square or cubic lattice. We take the phonons to be an Einstein phonon, some dispersionless phonon. We look at the most local possible coupling between the phonon displacement and the local electron density. The dimensionless electron-phonon coupling constant is then defined in terms of the coupling constants in our model. There's, if those of you who know about measurements of lambda, there's a bare lambda and there's a renormalized lambda, which is this quantity with this being the renormalized phonon frequencies measured on the Fermi surface. Okay, if you don't know, this is just a technical aside. I will talk both about the bare and renormalized lambda. And then we can solve this problem in the physical limit of the phonon frequency much smaller than the Fermi energy, and we find a phase diagram. And the interesting thing about this phase diagram is that normal metal behavior and superconductivity, by the way, are both confined to regions of relatively small lambda. And when we go beyond lambda small, something new happens, which is not a metal. So there's a pronounced crossover from Fermi liquid-like regime when lambda is smaller than something to a classical bipolaronic regime where the electrons form new sorts of quasi-particles. It's a bound state of electrons and a whole cloud of phonons. And these things, this is not a BEC to BCS crossover. These bipolarons are more or less infinitely heavy objects. They're classical objects, and they can't conduct. So, and in terms of this renormalized parameter, in all of our numerics, this always occurs for a characteristic lambda. This is now the renormalized lambda that's around 2. So that's very suggestive that when you tell me you're doing measurements on a metal, without knowing it, you've also told me that lambda is smaller than 2. And therefore, the T-linear resistance that you're going to see is bounded above. It's bounded above by this with lambda equals 2. This is nothing to do with a Planckian bound. It's nothing to do with thermalization. It's a stability bound on the stability of the metallic state itself. So it's the scattering rate that occurs at the crossover from weakly interacting, highly quantum, electron-like quasiparticles to weakly interacting, nearly classical bipolarons. Right, so that's our proposal. We can do measurements in this model. Here is a measurement of the resistivity as a function of temperature for some version of this model. What I'm showing you is the power law exponent on the resistivity. So here, the resistivity is metallic with a exponent like 1, that is to say T-linear resistivity. And here, where lambda is bigger, the exponent is negative, that is to say the system is behaving like an insulator with a resistance that's growing as we lower the temperature. So I think I'm more or less out of time, is that right? Okay, so let me skip this. And so now, since Jan Zanen can make spectacular conjectures that you should understand conductivity of metals by an ADS-CFT correspondence with the physics of black holes, I'll make what sounds like a rather modest proposal that when interactions are too strong, that either leads to a phase transition to a different state of matter, a different structure, or to a rearrangement of the quasiparticles in the system to a new type of quasiparticle, again, weakly interacting, but in some dual variables. And that this implies bounds on various quantities, transport scattering, actually also the superconducting TC. Okay, so that's the end. Can I have 1 minute? Okay. Let me tell you what I would have told you if I hadn't been told that this was a colloquium. So, first place, I would have explained the second statement that when the electron-phonon coupling is strong, all you can possibly get are insulating charge density wave commensurate phases at low temperature and insulating behavior at elevated temperature. There are no other options. However, we also have found that this old and hoary problem in condensed matter physics, the electron-phonon problem, has lots of unexplored territory in it, which occur at intermediate coupling or when combined with strong electron-electron interactions. And we have a number of works exploring this. in particular, so far, we've identified limits of this problem, which has a new type of superconducting state called a pair density wave, and in which deconfined fractionalized anyons can exist along with emergent U1 and Z2 gauge fields. All right, and with that, I will really end.
Could you just in qualitative terms explain what the physics of the quantum of resistance is? Like, should I be thinking about what an electron does when it has this resistance?
So, so the nice thing about dimensional analysis is that it allows us to make statements without knowing anything. And it also, I will give a better answer, but that really is the answer, is that, and moreover, it allows us to identify places where we really should be thinking hard about new physics. When things come out to be the quantum, there's nothing actually that much to describe. I mean, maybe there is, okay, so the binding energy of hydrogen is on the order of the quantum of energy. On the other hand, it was spectacular that you could calculate the binding energy of hydrogen precisely. That wasn't a minor step in the history of physics. Okay, so here too, if I could calculate the resistivity of liquid mercury quantitatively, I would be very happy with it. But I can estimate it without doing anything. Okay, so what does it mean? Well, roughly what it means is that it's at the bound of where quasi-particle pictures make sense. So you start turning up scattering, and once the mean free path gets to be on the order of the wavelength, then details of the scattering no longer matter. So, in liquid mercury, you have atoms all over the place, they're not organized. So of course the mean free path is on the order of the spacing between electrons. Between atoms. The actually surprising thing, the thing that comes out of Bloch's theorem, is when the atoms are arranged in a crystalline lattice, that the mean free path is infinity. Okay, so it's really the resistivity of metals that have much lower resistance that have some spectacular physics behind them. And the resistivity of mercury is sort of ordinary. Now, look, people have worked hard to try to understand, the temperature dependence of the resistivity of mercury. It changes by 30% as you go from the freezing temperature up to, I don't know, whatever temperature they explore. You would like to understand why it's temperature dependent, and there are theories about how that relates to variation of the liquid structure factor. But, basically it's that the quasi-particles scatter every time they go one atomic distance.
When I was a student on the go, we had the model of a free electron gas, which surprisingly gives the right value, for instance, for the resistivity of copper, at least in the same range. Is it just by chance?
So, I wish I knew a good answer to that. So, so again, there's a theoretical construct that we do, which is that if we start with free electrons, turn on a potential due to the periodic, the presence of a periodic lattice, but if we assume somehow that potential is weak, then we do what's known as nearly free electron theory. And for instance, this Fermi surface of copper can be computed extremely well from this perturbative approach. And one of the features of this perturbative approach is that although the topology of the Fermi surface actually changes in extremely vivid ways, rather than being a sphere, it has all these necks and shoulders and so on. So it's not that it does nothing, but in terms of quantitative things like the effective mass and it doesn't have very much effect. So if you're willing to accept that I can take a perspective from treating the periodic potential of the atoms as weak, I can answer your question. On the other hand, the periodic potential of the atoms isn't weak. And so then, I don't know, it's just an unusual robustness of these numbers. And it's not always true. There are some materials where the effective masses are 1,000,000 times the free electron mass. So, it's not universal, but there are actually quite a few materials where treating them as free electron gases works pretty well. I think that's mysterious. Okay, or I'm as confused about it as you are.
So Steve, so I had one question about this, the line that you showed where there are conventional metals as well as the more strongly correlated materials. All of them lie on that one plot that you were showing us from Andy McKenzie. And so, oh, whoop.
Went the wrong way, I guess.
And so here,
Well, all right, well,
yeah.
okay. You can see it even if it's not
Yeah.
full
So,
screen.
so what I wanted to ask was here, so the idea here is that the physical mechanism that allows for this resistivity to be linear. So is the claim that all these are bad metals whose slope can be understood? Was that the point you're trying to make?
No.
With
So, okay, so there's a lot of analysis that goes into getting this. Some of it is undoubtedly quantitatively wrong. But what's done here is to take various metals, so conventional metals here, cuprate high temperature superconductor here, organic superconductor here, strontium ruthenate that we already saw here, some heavy fermion materials. Also, so the red things are red because they're interesting, according to Andy. The blue things are boring because they're conventional metals, but Andy is an honest enough scientist that he put them all together. I don't know why it's not going to full screen, but and so all of these have resistivities that are way less than the quantum of resistance. But the coefficient of the scattering rate is roughly 1. So this is just, now, you can't go directly from the resistivity to the scattering rate. You need some Drude weight or compressibility. And so there's some funny business here. There's a well-defined experimental procedure that he followed, but there are many, in detail, there's ways of criticizing that. So these numbers are subject to some uncertainty associated with how the scattering rate is extracted from the resistivity. And these are all, as I said, much lower than the quantum of resistance. This goes from well above to well below, and many of these are around the quantum of resistance. So it depends on where you are in this phase diagram.
Thanks. Actually, I have a follow-up question while we're on this plot, because it is extremely provocative to see all these different materials on this one line. So do you know, is this a fairly representative sample of many different materials, or is it sort of carefully selected to show this nice grouping of around one?
So, so knowing Andy McKenzie, I think the answer is these are all the materials where he could get data that he completely believed. He's very skeptical of data, and so it's definitely very limited. All of these, with the exception of the cuprate and the iron nictide, are stoichiometric materials, and he really doesn't like alloys. So there's presumably is some bias here, but it's not bias in terms of looking for materials that fit. It's looking for data that's believable. Yeah, so I showed you on my, oh, this isn't going to work. Oh, it is. Okay, so here among conventional metals, okay, so first place, you may notice that there is a quantitative discrepancy between this table and that plot. So according to Andy, copper has an alpha of about 1. That's okay, because 0.13 times 2 pi is really pretty close to 1. But lead also has an alpha that's close to 1. And 1.5 times 2 pi is actually more like 10. And so the reason his lies closer is that he used, for this compressibility, he used low temperature thermodynamic data to estimate the compressibility, whereas in these, they used normal state calculated Drude weights to extract lambda. So I think these numbers are quantitatively better, and so you should use that as a level of uncertainty in interpreting the plot. But then you can also notice that here, 0.05 even times 2 pi is quite a bit smaller than 1. So there's a range. These lambdas range, well, from 1/20th to 1.5, so by a factor of 30. So these lambdas actually have quite a range. The thing that's notable is they sort of cluster at some upper bound. So I think this bound is perhaps more serious. Although this only includes conventional metals, because I can't make a plot like this for any of those unconventional red dots.
So I think we have to wrap up. So let's thank to Steve Kivas again.